In this video, let's learn how we can design a gated SR latch. In the previous video, we saw how we can design the circuit for the SR latch using NAND gates, and then we derived the state table. And also here I listed again the truth table for the NAND gates with two inputs. So the circuit for the gated SR latch. So we start by drawing the circuit very similarly to the SR latch using NAND gates. So we have two NAND gates, and then the top one will output the Q state, and the bottom one in the literature you see it called. And here we need, for the gated SR latch, we need two more NAND gates, and then they're connected through a gate. This is our gate. And then the top one will have the set input, and the bottom one will have the reset input. And then this NAND gate output will be one input of the top NAND gate, and then this will be here for the bottom NAND gate. And then a Q will be feedback to this bottom NAND gate, and P will be feedback to the top NAND gate. So this is the circuit for the gated SR latch. So now we want to see how we can derive the state table of the gated SR latch. So we have three inputs. We have a G, R, or let's see, G, S, and R. And we have the current state of the system, Q. And then we want to find out what is the next state, Q plus. So GSR, we will have 8 different combinations because of 3 inputs. So let's assume first in the first 4 rows, let's assume in G, the gate is 0, not enabled. So SR will have 0, 0, 0, 0, 1, 1, 0, and 1, 1. And then the next 4 combination, let's assume the gate is enabled. And then we have same thing, 0, 0, 0, 1, 1, 0, and 1, 1. So first let's analyze our circuit when the gate is disabled. So let's see. So when G is 0, this is G, let's make some space. When G is 0, so the top NAND gate will output, we have 0 and S. So let's keep S a generic. So the top NAND gate, we have 0 NANDed with S. So this will give us 1. And then the bottom NAND gate, same idea. So we have 0 NANDed with R. So 0 NANDed with R prime. So this will give us 0 NANDed with anything. The output is 1. So here we have the output is 1, and top here we have the output is 1. Now looking in this circuit, so when S bar is 1 and R bar is 1, we see the next state is the same as the previous state. So that's why we say hold the last state. So when G is 0, regardless of what S is and what R is, the next state will be always equal to the previous state. So for the first 4 combinations, we'll have Q, 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 Q. That's why we say hold. Hold the previous state. Now let's see what happened when the gate is 1. So when G is 1, so let's see what will be the next state. So now we have a G is 1. So the top left NAND gate, we have S NANDed with 1. So the S NANDed with 1, and then for 0, 1, we can have 0. And then for 1, 0, we can have 1. And the last one is our invalid. So that's it. So we can rewrite our state table in a simplified way. So we can have a G, S, R, and then we have the next state is Q plus. So first, when G is 0, we don't care about what S is and what R is. We will always get we will always hold the previous state of the system. When G is 1, we have 4 possibilities. It'll act same thing as the SR latch using NAND gates. So we have 0, 0, we hold the state, 0, 1, we set it to 0, 1, 0, we set it to 1, and then 1, 1 is our invalid. Thanks for watching. I hope this was helpful.